Teaching fractions from concrete objects to abstract math. Welcome to this explainer. Math often gets a bad rap for being a bit too abstract, right? But today, we're skipping the dry theory. Instead, our entire focus is going to be on teaching foundational math through highly physical, everyday objects. Let's get right into it.
So, how can we teach math so it can be seen with the naked eye? Well, when introducing fractions, the magic truly happens by jumping straight into hands-on demonstrations. We need to physically ground the math before ever looking at a number.
And slicing a real, tangible apple into two equal halves is absolutely the perfect first step. Taking a real-world object and firmly cutting it directly down the middle creates this instant, undeniable visual of one half. Notice there are no equations here yet. It's just a whole object physically separated into two perfectly equal parts. We can see that exact same satisfying principle applied to cutting a cake. Splitting a delicious sponge cake right down the center really hits home that fractions are literally everywhere in daily life. Plus, it forms a mouth-watering baseline for learners, especially when talking about sharing food fairly.
Moving on to practical activities creating fractions. Once that physical, food-based context is set, these ideas translate incredibly well into accessible classroom activities.
Let's start with a simple square piece of paper. Folding it directly down the middle creates a very clear crease. Unfolding it, or even cutting along that line, clearly produces two equal halves. It turns an abstract mathematical concept into a highly tactile physical experience.
Applying this same action to a rectangular paper shows some really consistent results. Whether folding it straight across or diagonally to form two triangles, the action always yields two equal parts. This proves that the fraction, 1/2, applies to any whole unit as long as it's divided equally. Finally, firmly folding a circular piece of paper solidifies the whole foundation. It doesn't matter if the fold is vertical, horizontal, or diagonal, the result is always two equal semicircles. Through the physical acts of cutting apples, slicing cakes, and folding various geometric shapes, the core concept is flawlessly established. Now, for the definition and parts of fractions, it is absolutely crucial that formal mathematical terminology is introduced only after visually understanding these physical parts. The key is tethering those physical halves directly to the new terms. The top number, the 1, is the numerator, representing the specific parts taken. The line is simply the fraction bar, and the bottom number, the 2, is the denominator, representing the total number of equal parts.
Because of all that physical grounding, the formal definition becomes completely intuitive. A fraction is just the division of an object or thing into perfectly equal parts. Starting with concrete examples like the apple and the paper makes this definition make complete logical sense. Next up is knowing fraction types, where we categorize fractions based on their size relative to one whole unit.
First, we look at fractions smaller than one complete unit. Take 4/10 or 5/6. The numerator is visibly smaller than the denominator. This makes it instantly apparent that the highlighted portion is just a piece, less than a complete whole. But what happens when the numerator and denominator share the identical number? Well, these pizza visuals prove that the pieces form one complete unit. Two halves, or 3/3 of a pizza, piece together perfectly to make one whole pie. It brilliantly shows that 2/2 is quite literally just a different way of writing the number 1.
Conversely, fractions larger than 1 occur when the parts we have exceed a single shape. To represent a larger numerator, multiple whole units actually must be drawn out. It is a fantastic visual representation for numbers greater than 1.
Let's move on to operations on fractions. With a solid grasp of what these numbers represent visually, we can start performing actual math operations without ever relying on rote memorization. Bridging perfectly back to our opening, adding fractions with the same denominator is as simple as putting an apple back together. Adding one physical half to another half undeniably equals one whole. It perfectly mirrors the numerical equation in real life. For subtraction, the exact same visual logic applies. Starting with the pie divided into sixths, let's say 4 pieces, and physically removing one leaves exactly 3 pieces. This flawlessly explains to learners why the denominator remains completely unchanged during simple addition and subtraction. Now, adding fractions with different denominators, like 1/4 and 2/3, usually gets a bit complicated. However, drawing visual grids completely eliminates the confusion. Overlaying a horizontal grid with a vertical grid demonstrates how to literally slice the shapes further to find a common base. In this specific case, it creates 12 equal squares. This brilliantly reveals that even complex addition, such as 2/3 plus 3/5, can be solved using this visual method. Merging a 3-part grid with a 5-part grid automatically creates a common denominator of 15. It makes a traditionally abstract algebraic process completely visibly understandable. By grounding every single lesson in the tangible world first, starting with the satisfying slice of an apple or the simple fold of a paper square, mathematics is never just memorized. It is truly seen, felt, and understood. When invisible concepts are made visible, the fear of math simply disappears. Which leaves us with a lingering, exciting question. If complex fractions can be mastered with an apple and some paper, what other supposedly difficult mathematical concepts are just waiting to be uncovered in our everyday environment?